good day. This is a first presentation on computational complexity studies on the robust design and scheduling of batch chemical processes. I am João Miranda, professor at the Escola Superior de Tecnologia e Gestão at the Instituto Politécnico Portalegre, and researcher in CERENA, Centro de Recursos Naturais e Ambiente at the Instituto Politécnico. Thanking you for the attention. This is a course session on the mathematical and computer science methods for food science and industry. And for that, I would like to present my acknowledgements to the course association, and thank you for their support. Also thanking Professor Jan van Impe from the University of Leuven, and all the enduring support from Philip Cherry from Eurosys. Of course, the Portuguese Science Foundation, Fundação para a Ciência e Tecnologia, and thanking also the Instituto Politécnico Portalegre and CERENA Institute Superior. I thank them all for the enduring support and to these works. And the agenda for the presentation, a brief introduction, of course, in the end, the conclusion and further development. The second step for the multiple machine and single product campaign, the complexity study, that are enlarged for the robust framework in the third step. So, just revisiting the problem on the scheduling of batch process. This is a full shop problem. One machine per stage, one machine per job, and one job per machine. This is a relation 1-to-1 with a number of applications on manufacturing, on mechanics, electronics, and of course in chemical batch process. Typically, the maximization for the utilization of the equipment can be also related with the minimization of mix spend, and of course the food industry, pharmaceuticals are typical applications. And the specific problem for design and scheduling of chemical batch process is studied by Buduris and Grossman, and then it is also generalized and enlarged in several works that is related the flow shop, the scheduling and the design, but the job shop is not addressed in these developments. Just revisiting briefly computational complexity from Gare et al., and that looking for the worst case, applying the best possible algorithm over all the possible instances. This can lead to further developments on the heuristics and numerical enhancements, in the sense that we know better the problem and we can use, let's say, one approach, one algorithm that works well for the knapsack problem can be used for the design and schedule problem, because it works well with knapsack, so then it can work well also with the design and schedule. This is more or less the idea for the computational complexity issue. So, looking for the multiple machine and supply and single product campaign, and revisiting the deterministic models for the single machine and single product, SS, the multiple machine and single product campaign, MS, and combinatory single machine multi-product campaign, SM, and multiple machine multi-product campaign, MM. And these are studied in the last year for the 08 process flow shop problem. And in this work in 2019, the idea is to convert the optimization problem in a decision problem. A decision problem that requires a decision yes or no. In that sense, we have restricted the problem to only two stages. The two stages decision problem, and then restricted to the three partition problem. It is showed condition, necessity, and also sufficiency. In this way, the decision problem for single machine, single product, two stages decision problem is also should demonstrate it is an NP complete problem. In that sense, then the single stage, single machine, two stages is also NP hard. And finally, the SS problem is also NP hard in strong sense. So we are enlarging the approach to the multiple machine, single product, and once again this restriction approach, polynomial approach, can be very simply restricted to one single machine, and the problem MS1, that is the multi-machine problem, but considering the restriction to one single machine, is the same problem and equivalent to the single machine, single product campaign problem. So in this way, we remember also the data for the problem, the number of products, the demands, quantities demanded, the time horizon, the set M for stages, the set M for equipments. Note that each equipment can present a number of sizes, the discrete sizes that we are finding in industry, and also the size factor with relating the volume and the mass in each equipment. Also the processing times, T, related with the production of each product. So remember here the problem for multiple machines in product campaign, minimization of costs, binary variables, 0, 1. The definition for the number of batches, n. The binary variables, only one is positive, all the others are 0, nil. The sum of production times below the horizon time. The definition for the production time for each product. Remember the binary variables, only one of the number of cycles is positive, all the others are 0, and summing all the number of cycles we obtain the total number for each product E. The definition for the continuous variables and also the binary variables. So we have the model in the equations too, and it is straightforward that single product, single machine is a special case of the multiple machine. So the multiple machine and single product campaign problem is NPR. So it is also obtained, developed several heuristics and generalized to a robust framework. In this way, we look in this step 3 for the robust problem and doing the computational complexity study. Once again, a decision problem, but now with the uncertain demand in a multi-period framework. In this way, we have a large model with the sum of the probabilities and the net value. Please note the return minus the costs, so the net value, and minus penalizing the variation, the negative variation, and also penalize the quantities not satisfied, and also penalize the slack on the capacities. Let's see more in detail. The value is the sum of the return of all the productions minus the costs of all the equipment. In this way, the deviation negative is penalizing the values that are below the average. This sum represents the average value for the production scheme. Note that in equation 3, in equation 3D, we have the production below the quantities. This is a flexible scheme, since the slack on the inequality is represented now by the variables for non-satisfied quantities. The same for the volumes, the equipment that are not used. We have in the left side the production, the size factor that must be below the volumes of the equipment. This is represented by the capacity slack, this variable, and this is similar to the further equation for the number of cycles disaggregated, the logical relation. Only one of them is positive, the other are nil, as follows from the binary variables, and it implies in the same way that number of cycles is disaggregated, is defining the total number of cycles. In this way, for the same part, the production times and sum of production times below the horizon time. So typical equations, typical relations for the variables. In this way, the computational process, in a restriction to only one random scenario, restriction to one single time period, by penalizing the parameters made nil, the same for the product returns, so the objective functions are equal and both problems present equivalent solution place. Let's see the problem only one scenario, only one time period. Note that return is not present in the objective. This slack variable is transforming the less than inequality in a equality relation, binary variables, the time horizon relation, the time campaign time definition. So the equations 8 are similar, are equivalent to the equations 2, and the same for the definition of number of cycles, the semilogical variable, and also the definition of the aggregate number of times. In H and I, the variables definition. So theorem 2 follows that the problem, robust problem, has a feasible solution if and only if problem MS has a feasible solution, and then the corollary: for one only random scenario, one time period is NP-hard, and then the problem is NP-hard in the strong sense. In this way, we are concluding the presentation, just firstly revisiting previous works from 2019, addressing the flow shop and zero weight policy, and these problems, the deterministic problems, are NP-hard in strong sense. Now it is shown for the robust problem, stochastic and robust problem, raw batch MES is also NP-hard in strong sense. And these studies allow the certification of numerical implementation, development of heuristics, and also further generalizations for multi-criterion decision making, as the reference from Benamor et al. Can present. We have the reference in here from the advanced studies in MCDM, published in CRC Press in December 2019, and also the other reference of interest. Thank you for your attention, and please send me your questions. Thank you.